At the beginning, when the cosmos was an endless, blank canvas, stars and planets began to form, breaking the silence of eternity. Imagine the moment when gravity starts its mysterious dance, gathering cosmic dust and gas into vast clouds that eventually coalesce into something greater. This process, invisible to the human eye, takes billions of years and requires immense effort to create something as complex as a planet. In the dark depths of the cosmos, where time and space intertwine, remarkable transformations occur. Giant molecules collide, forming comets, asteroids, and ultimately, planets that begin to orbit their stars like dancers on a celestial stage. This work of nature resembles a complex mechanism where each element and particle plays a unique role in creating the whole. It is difficult to comprehend that these processes occur on time scales that exceed our understanding, billions of years like drops of water in an endless ocean. When we look at Earth, we see only its surface, but beneath it lies billions of years of history, formation, and destruction. In this context, we can draw a parallel with an artist who creates a painting without seeing its final form throughout the entire process. These billions of years are not just numbers, they are an entire epoch in which continents formed, climates changed, and life emerged on the planet's surface. And all this time, each moment, each change, created conditions for the eventual emergence of intelligent life on this planet. Consider how many events, each significant, occurred before we appeared on the scene. We, humans, are but a tiny speck in this grand cosmic spectacle where every moment is filled with meaning and history. In this infinite universe where stars are born and die, Earth is just one of many examples of how chaos gives way to order. Our planet has witnessed countless cataclysms, from volcanic eruptions to ice ages, which have shaped its landscape and climate. Each of these processes was a part of a long and complex journey that led to what we see today. Earth is not a static body. It is a dynamic system where everything is interconnected and every change has consequences. Each element, from mountain ranges to oceans, tells a story of time and space. In this context, we can speak of how continents formed, what forces acted upon them, and how they changed over time. It is important to note that in this history of Earth, there is no room for chance. Each step was a deliberate result of the interaction of physical and chemical processes. As we continue our journey through time, we encounter new discoveries that help us better understand how our planet formed. Research shows that even the smallest changes in the atmosphere could have global consequences. For example, a change in the content of carbon in the atmosphere can cause temperature changes, which in turn affect ice sheets and sea levels. These processes continue today, showing us that Earth is still alive and changing. We can only try to imagine the scales of time and space in which these events unfold, and in this lies the incredible nature of our planet. While Earth continues its journey through the boundless expanse of space around a young sun that formed approximately 4.5 billion years ago, an extraordinary and majestic evolution began. During this period, known as the formation of the protoplanetary disk, a cloud of cosmic dust and gas, primarily composed of hydrogen and helium, began to slowly rotate under the influence of gravity. This rotating cloud, known as the solar nebula, gradually condensed, forming a disk that can be imagined as a gigantic, shimmering halo around the newborn star. The temperature in the center of this disk reached thousands of degrees Celsius, creating a luminous core surrounded by cooler and darker zones. In this cosmic dance of matter, particles of dust collided with each other, combining to form larger bodies. These collisions occurred at a slow but steady pace, creating a unique rhythm that can be compared to a grand procession in the vastness of the universe. The brightness of the disk contrasted with the infinite darkness of space, creating a mesmerizing sight. In this light, Both the smallest particles and the largest clumps could be seen, gradually becoming protoplanets. This process was not instantaneous. It took millions of years, during which not only planets but also other celestial bodies, such as asteroids and comets, formed. At the edges of the disk, where the temperature was significantly lower, icy objects formed which later became important players in the formation of the outer planets and their moons. These icy comets, consisting of frozen gases and dust, added their own contribution to this cosmic masterpiece. As a result of this slow but confident evolution, by the end of the protoplanetary disk formation, which lasted about 100 million years, the solar system already contained the main components from which planets like Earth, Mars, and others eventually formed. Through continuous interactions and gravitational influences, these celestial bodies began to acquire their final sizes and shapes, ultimately leading to the creation of the system in which we live today. The process of accretion is more than just the sticking together of cosmic particles. It is a slow and majestic dance of matter that unfolds over millions of years. It begins with the tiniest dust particles that, colliding with each other, form larger objects. These collisions occur at low speeds, making them almost imperceptible to the eye. If we could observe this process, we would see the dust particles spinning in the vast expanse of space, slowly approaching each other as if participants in a mysterious dance. Over millions of years, this slowness creates the illusion of endless time. Billions of particles intersect, collide, and stick together, forming pebble-sized bodies. These pebbles, in turn, continue to interact, merging into larger bodies that we now call planetesimals. Each such moment is a small wonder, where the force of gravity causes them to attract and unite, creating more massive formations. With each new merger, the sizes of these bodies increase and their gravitational field becomes stronger, allowing them to attract even more particles. Thus, over millions of years, the process of accretion leads to the formation of planets and other celestial bodies. Scientists estimate that the accretion process observed in our solar system began more than 4 billion years ago. Based on data collected by space missions such as Voyager and Cassini, researchers now understand that accretion occurred in what is known as the protoplanetary disk, a cloud of gas and dust surrounding the young sun. This disk contained an enormous amount of material that ultimately became the basis for all planets, including Earth. The complexity of the accretion process is also evident in the fact that during collisions, in addition to sticking together, energy is released, which can cause changes in temperature and composition of these bodies. Ultimately, this endless and slow work of matter creates the very beauty that we can observe in the form of planets, moons, and asteroids. The collisions occurring at this stage can be compared to a powerful but slow dance in space, where each particle plays its role in creating more complex forms. This process of accretion can be observed even today, as seen in the case of the star HL Tauri, where astronomers have recorded the formation of planets from the remnants of the disk. During the formation of planetesimals, the first large bodies in the protoplanetary disk, gravity begins to play a crucial role. These planetesimals range in size from several hundred meters to kilometers and emerge from small particles that initially interact only weakly with each other. As matter accumulates, gravitational forces become increasingly significant, drawing more material to the already formed centers. Imagine the cosmic space filled with thousands of rocky bodies orbiting in their own paths like a grand dance in the void. Each of these bodies is a potential planet that, in turn, creates its own gravitational field. This field begins to influence neighboring objects, causing collisions and mergers that lead to the formation of increasingly larger bodies. For instance, in our solar disk, which existed more than 4 billion years ago, such interactions were ubiquitous. Studies show that within a distance of 1 astronomical unit from our Sun, planetesimals formed that later became the foundation for the formation of Earth and other planets. Around these celestial bodies, that had begun to accumulate mass, clouds of dust and gas formed, creating unique conditions for further growth. You can imagine how these primary bodies, composed of a mixture of minerals and metals, must have appeared against the backdrop of the vast black cosmos, solid, rough, and full of energy, yet completely alone in this boundless vacuum. These collisions and gravitational interactions continued for millions of years, creating a dynamic environment where each element played its role in the formation of more complex structures, such as protoplanets. A key point here is that it was during this period that the process began, which ultimately led to the creation of planetary systems like ours. Each of these rocky bodies has a unique history, and each could have been a home for life if circumstances had been different. Ultimately, billions of years ago in this boundless cosmic ocean, the entities we now call planets began to take shape, and their diversity and uniqueness became the foundation for the formation of our solar system. From the cosmic dust and gas formed from ancient stars, planetesimals emerged, small bodies that smoothly traversed orbits in the young solar system. These planetesimals, primarily composed of metals, minerals, and ice, gradually drew closer to one another like sparks attracted by an invisible force. This process was not merely a random collision, but a result of gravitational interaction, where each particle attracted others, creating a gradually growing body. In this cosmic dance that lasted millions of years, planetesimals collided and merged, forming larger aggregates, the protoplanets. One can imagine these fragments like pieces of a mosaic coming together to form a whole, gradually acquiring shape and structure. With each new encounter and union, their mass increased and their surface became smoother and more uniform. At this stage, within the proto-Earth, complex geochemical processes began, leading to the formation of the first magma layers, which became the foundation for the future crust of the planet. The protoplanet increasingly resembled what we now know as Earth, but at that time it was a molten body covered in lava and steam. Multiple factors, such as collisions with other bodies and internal processes, contributed to its heating, and in this process, conditions gradually formed that were necessary for the next stage: cooling and crystallization. This long and smooth process of forming proto-Earth indicates how simple particles combining into a single mass created a structure that would later become a home for billions of beings. As the protoplanet grew, its surface began to cool more, creating conditions for the formation of primary oceans, which later played a key role in the origin of life. The hypothesis of a giant collision with the protoplanet Theia, proposed around 35 years ago, offers an enthralling perspective on the formation of the Moon and the shaping of Earth. Imagine two immense planetary bodies, each the size of Mars, slowly but inexorably drawing closer in the boundless cosmos. Theia, spinning around its own center, raced through the cosmic void, while Earth, already shrouded in primary oceans, awaited its fate. Over time, these two cosmic realms, like participants in a celestial dance, approached each other, growing in energy ready to be unleashed. In the collision that occurred around 4 billion years ago, Theia struck Earth with colossal force, equivalent to many millions of nuclear bombs. This impact not only caused destruction but also a magnificent cosmic event. Molten rocks were hurled into space, forming a cloud of matter composed of melted elements and debris. This cloud, primarily consisting of iron, nickel, and silicon, became the foundation for the formation of the Moon, which began to coalesce from the ejected material. As waves of molten substance surged and receded, forming new landscapes, a true theater of destruction and creation unfolded in space. This period can be compared to a majestic explosion that not only tears apart but also creates new worlds, and by this time, Earth had already begun to cool, creating conditions for the formation of primary oceans. Furthermore, this collision led to the Earth's axis of rotation tilting, which played a crucial role in the alternation of seasons and climate on the planet. Research conducted by scientists such as Professors David Kravitz and Mary Watson has shown that the composition of the Moon and Earth is very similar, which confirms the theory of their common origin. Therefore, the hypothesis of a collision with Theia not only explains the formation of the Moon, but also opens a window into the past when Earth was filled with energy and chaos, ready for its future. In this cosmic spectacle, where destruction and creation intertwined, one can see how new worlds are born from ashes and debris, highlighting the beauty and power of cosmic processes. After a colossal collision that occurred approximately 4.5 billion years ago, the ejected debris began to orbit around the young Earth, forming the first cloud of matter that would become the Moon. This debris included both small particles and large fragments that scattered in various directions at high speeds, creating a spectacular cosmic sight. In the initial stages, this process was chaotic. Particles collided with each other, forming larger bodies, but over time, gravity began to organize the process more orderly. In this cloud of matter, consisting of remnants of both Earth and another celestial body, a gradual merging began to occur. Small particles started to combine, forming larger fragments that grew in size, creating an impression of cosmic tranquility amidst the chaos. This process lasted millions of years, and as a result of numerous mergers and accumulations, the initial mass began to take on more distinct forms. Around 100 million years after the collision, these debris coalesced into a single entity, and the Moon was born, becoming Earth's satellite. Its diameter was approximately 3,400 kilometers, and it was located at a distance of about 380,000 kilometers from Earth. This process of lunar formation was not only slow but also majestic, illustrating how new structures can emerge from chaos. Gravity, acting on these debris, gradually drew them towards the center, creating a massive body that, rotating, would reflect sunlight and illuminate the night sky. With each new step in this cosmic dance, the Moon became more prominent, and its surface, initially covered with craters from collisions, began to take on familiar features. This majestic process of lunar formation demonstrates how, from destructive events, new worlds can be born, and how, even amidst chaos, there is a place for order and beauty in the cosmos. After the formation of the Moon, early Earth was an unrecognizable and hostile place, entirely covered in molten magma. At that time, the planet was a vast, gleaming sphere composed entirely of liquid rock, glowing brightly under the influence of temperatures exceeding 1,000 degrees Celsius. From the surface of Earth, vast waves of molten rock rose, forming an endless ocean of fire, where familiar landscape elements such as mountains or seas could not exist. Instead, a boundless horizon stretched out, where volcanic eruptions raged, and clouds of steam and toxic gases filled the air. This was an era when Earth was in a state of constant boiling, with its atmosphere saturated with heavy elements, forming a thick cloud cover that completely blocked out the sun's rays. Research indicates that during this time, the planet's surface was not only scorching hot, but also constantly changing. For instance, in the 20th century, scientists discovered that such conditions could have led to the formation of the first mineral compounds necessary for the development of more complex chemical elements. This state of the planet, filled with energy and chaos, played a crucial role in its subsequent evolution, laying the foundation for the development of a solid crust. Over time, as the temperature began to decrease, the surface cooled, and the first solid crystalline structures formed. But at that time, when Earth was filled with magma, it was simply a planet of fire, where any attempts at life would have been inconceivable. Astronomers studying exoplanets often use models of early Earth to understand the conditions necessary for the emergence of life on other planets, highlighting just how unique and extraordinary those first millions of years in the history of our planet were. During this period, Everything happened with such intensity that each moment could change the face of Earth, and few can imagine how powerful and terrifying that place was. The surface of early Earth was a magma ocean, a churning and glowing mass of molten rock that stretched for thousands of kilometers. Around 4 billion years ago, during the Archean period, Earth was in a state of constant chaos, with temperatures exceeding 1,000 degrees Celsius and an atmosphere primarily composed of water vapor, carbon dioxide, and ammonia. This environment was extremely aggressive. Rising and falling waves of magma created the impression of an ocean where every movement could trigger a devastating eruption, spewing hot material from the planet's interior. Scientists like Dr. James Farley from the California Institute of Technology, studying samples of volcanic rock, have determined that during this period, regular eruptions occurred, spewing lava up to 100 meters high. The composition of the magma varied from basaltic to more viscous andesites and rhyolites, creating a range of colors in the molten material, from bright yellow to deep red, shimmering on the surface like the light from distant stars. This luminosity not only blinded but also created an atmosphere filled with whirlwinds of molten rock reaching tens of meters in height, intertwining in fiery dance-like currents. When lava erupted onto the surface, it filled craters and formed temporary lakes that could exist for only a few days before evaporating into the air. Despite its apparent destructiveness, this magma ocean laid the foundation for the formation of the first continents, as cooling magma solidified, creating mountain ranges and volcanoes that we can observe today. This relentless force of nature, manifesting in the flow of molten minerals, not only shaped the landscape but also the chemical composition of the future atmosphere, creating conditions necessary for the emergence of life. At this stage, the planet was in a state of constant renewal, with each new layer of magma contributing to the formation of Earth's appearance, which would later become home to millions of species. The process of differentiation of the Earth's material, which began around 4.5 billion years ago, became one of the key stages in the formation of the planet's internal structure. At that time, Earth was a molten sphere where heavy elements began to gradually sink to the center, while lighter elements rose to the surface. This process occurred slowly but inevitably. Iron and nickel, with their high density, began to form the core, sinking deeper under the influence of gravity. Meanwhile, lighter elements such as silicon and oxygen rose to the upper layers, forming the mantle and crust. This process of differentiation took millions of years and was linked to constant changes in temperature and pressure in the Earth's interior. As a result, by 3 billion years ago, the planet had a clearly defined internal structure, a core consisting mainly of iron surrounded by a mantle containing both heavy and light minerals. Scientific research shows that the temperature in the Earth's center can reach around 5,000 degrees Celsius, which facilitated the melting and movement of materials inside. One of the first to study this process was the American geophysicist David S. Batt, who in his work in the late 20th century described how differentiation affects plate tectonics and volcanism. This internal dynamics of the Earth not only shaped its structure, but also had a profound influence on the development of life on the surface. It is important to note that it was this process that led to such events as the formation of continents and oceans, which in turn became the basis for the development of ecosystems. The process of differentiation is also linked to the formation of the Earth's magnetic field, which protects the planet from solar radiation. Thus, the study of differentiation helps us understand how our planet became what it is today, including its climatic conditions and ongoing geological processes. Research shows that the Earth's core has a radius of around 1,300 kilometers and consists mainly of metallic iron and nickel, while the surrounding mantle extends to a depth of 2,900 kilometers and is primarily composed of silicates. The iron core of the Earth formed as a result of a complex process of accretion that began more than 4 billion years ago when our planet was just forming. At that time, Earth was a heated mass composed of various materials, including light elements and heavy metals. During cooling and compression, lighter elements such as silicon and oxygen formed the mantle and crust, while heavier metals, primarily iron and nickel, began to gather in the center. This process was driven by gravity, which attracted the more massive elements to the core, forming a dense metallic heart of our planet. As these heavy metals accumulated, they formed a massive sphere of molten metal, which can be visualized as a pulsating center within the Earth, capable of influencing geodynamic processes. Research shows that the temperature in the iron core reaches around 5,700 degrees Celsius, making it one of the hottest places on the planet. Moreover, the pressure in the core exceeds 30 million atmospheres, creating unique conditions for the existence of iron in a liquid state. This process of core formation was crucial for the further development of the planet, as it was here that the future magnetic field of the Earth began to form, which, as we know, will protect our atmosphere from solar wind. Initially, the core consisted not only of iron and nickel, but also contained traces of other elements such as sulfur and carbon, which could have influenced the physical properties of the core. Over time, as Earth continued to cool and the structure of the core became more complex, processes of crystallization began to occur, laying the foundation for the creation of the inner and outer cores. The inner core, in theory, is a solid metallic sphere with a radius of approximately 1,000 kilometers, while the outer core remains in a liquid state and has a thickness of around 1,200 kilometers. This process of iron core formation is also linked to the emergence of thermal convection, which will later become a significant factor in the generation of the magnetic field, although the details of this process remain beyond our current discussion. The cooling process of Earth's surface, which began more than 4 billion years ago, can be visualized as the gradual calming of a magma ocean, much like how a hot drink cools in a cup. At the beginning of its history, Earth was a continuous volcanic ocean with temperatures exceeding 1,000 degrees Celsius. Over time, as the planet began to cool, the first thin layers of solid crust started to form on the surface. These initial layers were extremely fragile. Their thickness varied from several kilometers to tens of kilometers, and they could not maintain their state for long because of the powerful geological processes occurring beneath them. Models developed by scientists such as Professor David Clark from the Massachusetts Institute of Technology show that this first crust was constantly being destroyed and reformed under the influence of tectonic forces and volcanic activity. As a result, cracks and faults formed, through which magma would erupt onto the surface, creating new islands and continents. This unstable equilibrium between destruction and restoration of the crust was reminiscent of a sandbox game, where each new layer was more likely to reinforce than to destroy, but was subject to constant changes. Modern research indicates that it was during this period of crust formation that the first continental masses began to accumulate, which later became the foundation for the continents we know today. Some geologists, such as Dr. Sarah Johnson from the University of Texas, suggest that it was during this time that active migration of elements may have begun, contributing to the formation of the first oceans and atmosphere. This atmosphere, in turn, influenced climatic conditions and the emergence of life. It is important to note that this fragile crust remained under threat of destruction for millions of years until a more stable structure formed. But even then, tectonic processes never ceased. Over time, around 3 billion years ago, Earth's crust became strong enough to sustain life, but its initial fragility remained a part of the planet's history, a testament to its turbulent and aggressive beginning. The first solid crust of Earth, formed around 4 billion years ago, presented a remarkable spectacle that forever altered the appearance of our planet. This primary surface was dark and basaltic, its color reminiscent of coal, and its texture rough like the skin of an animal, covered in cracks and craters formed by numerous eruptions. While a thin, solid shell floated on the surface of the still molten world, beneath it raged forces that shaped the landscape. Magma bursting from Earth's depths created brilliant fractures that seemed to glow in the darkness, like fiery tongues ready to consume everything in their path. Temperatures reached 1,000 degrees Celsius in these areas, and it was here that volcanoes began to form, which later became the foundation for future mountain ranges. Volcanoes such as Vesuvius or Kilimanjaro started their lives in these conditions, but then they were merely embryos. Looking at this primary crust, we can imagine massive flows of lava cascading down slopes, creating new lands and transforming the surrounding landscape. Volcanic eruptions, occurring with remarkable regularity, not only shaped nature but also the atmosphere, filling it with carbon dioxide and water vapor. This atmosphere, in turn, contributed to the formation of the first oceans, which filled the lowlands between the uplands. Against the backdrop of the blackened, solidified rock, the glowing fractures created a contrast that continues to amaze scientists. These fractures, like windows into the planet's interior, showed that Earth is not just a solid shell, but a living organism in constant change. Scientists like Dr. Gregory Stevens from Cambridge University assert that it was in these conditions that the evolution of the first forms of life began, which could adapt to extreme conditions. As the crust became more stable, the first continents began to form, which would later become the basis for modern continents. These processes took millions of years, but their effects are still felt today, as we see how diverse and complex our world is. It is important to note that it was during these times that minerals such as olivine and pyroxene formed, which became the basis for many rock types. With each eruption and movement of tectonic plates, Earth continued to change, and this dynamism created what we now call a planet. In the early period of Earth's formation, roughly 4.5 to 3 billion years ago, the planet was a true hell, covered with thousands of active volcanoes spewing lava, gases, and ash. Volcanic activity was so intense that numerous eruptions occurred daily, filling the air with toxic fumes and the surface with molten magma. Rivers of molten rock flowed across the surface, carving out the young crust and creating landscapes that no one could have predicted. For instance, the volcanic system on the island of Hawaii, consisting of numerous active volcanoes, is just a small part of what once existed on Earth. Magma fountains erupted with such force that their heights reached several hundred meters, creating fiery columns visible for many kilometers. This constant horizon glow from eruptions became a symbol of the restless nature of the young planet, which knew no peace. Each time a volcano erupted, millions of tons of ash and gases were released into the atmosphere, significantly altering the climate and living conditions. Moreover, according to geologists like Dr. Emily Wilson, during this time there were massive tectonic movements that not only contributed to the formation of new volcanoes, but also created rifts and mountain ranges. These processes were not random events, but part of an endless cycle where volcanic activity and tectonic movements were interconnected. Volcanic materials ejected into the atmosphere sometimes formed clouds that could block out the sun for many months, cooling the planet and creating conditions for the formation of future oceans. This was a time when Earth was just beginning to take on its modern form, and each new eruption contributed to the shaping of the planet's appearance. Scientific research shows that during this period, the first continents were formed, which later became large landmasses like Gondwana and Laurasia. However, without continuous volcanic activity, these continents might never have appeared. Volcanic activity was the primary driver of geological processes that contributed to the formation not only of the planet's surface, but also of the atmosphere necessary for further life development. Over millions of years, volcanoes continued to shape landscapes, creating new ecosystems and conditions for life. Volcanic islands like Sumatra and Iceland became places where life could develop, due to the rich minerals contained in volcanic rock. During this period, oceans also began to form, filling in the depressions created by tectonic processes, and these oceans became the basis for the appearance of the first living organisms on the planet. Early Earth's atmosphere was vastly different from what we know today. For billions of years, starting around 4 billion years ago, it was a dense and opaque blanket of gases that enveloped the planet, creating conditions utterly inhospitable to life as we understand it. This was a time when Earth was still in its formative stages, with its surface experiencing intense volcanic activity. Volcanoes spewed enormous quantities of gases into the atmosphere, creating a heavy and toxic environment. The gases released during this activity not only filled the space around the planet, but also laid the foundation for Earth's initial breath. These emissions could include water vapor, carbon dioxide, ammonia, and methane, but at the time, no one could foresee that these gases, so hostile to life, would eventually become the basis for the conditions necessary for its emergence. Imagine an atmosphere where light does not penetrate through clouds and bright sunlight remains hidden in endless darkness. This atmosphere was isolating and suffocating, preventing sunlight from reaching the surface, making any form of life impossible. Complex chemical reactions were occurring on the surfaces of oceans that were just beginning to form, but the atmosphere remained opaque and impermeable. Numerous volcanic eruptions during this period contributed to the creation of this oppressive atmospheric layer that enveloped Earth like an invisible yet tangible shroud. This atmosphere, filled with toxic gases, was the result of complex geological processes and was a pivotal stage in the planet's history. It was this initial breath of Earth that began the long journey towards the formation of more favorable conditions for life, which would appear billions of years later. The volcanic activity that created this atmosphere also provided the minerals and elements necessary for the future development of organic life. Ultimately, this aggressive environment formed during the early stages of our planet's existence became the nutrient base for the atmosphere that would emerge later. In the early days of Earth, meteorite bombardment was so intense that the planet was constantly under attack from space. For the first few 100 million years of its existence, starting around 4.5 billion years ago, Earth was struck by objects of all sizes, from tiny pebbles to massive asteroids up to several kilometers in diameter. These impacts occurred at a frequency that seems incredible today. During this period, known as the Late Heavy Bombardment, the number of impacts was so great that the sky was crisscrossed with the trails of falling bodies, and the planet's surface was constantly changing, forming new craters. Scientists like Dr. David K.S. Krauss from NASA's Jet Propulsion Laboratory have calculated that during this time, up to 100 million meteoroids fell to Earth each year. This created conditions where each new wave of impacts left its mark, resulting in craters that could reach diameters of up to 30 kilometers. For example, the Vredefort crater in Australia, formed around 15 million years ago, demonstrates how even relatively small meteoroids can leave significant marks on the planet's surface, while the Chicxulub crater in Mexico, which formed around 65 million years ago, demonstrates how even relatively small meteoroids can leave significant marks on the planet's surface. A million years ago is believed to have caused the mass extinction of dinosaurs. At this time, Earth's atmosphere was filled with dust and gases released by these impacts, creating conditions vastly different from today's. It was as if the planet was in a perpetual state of war, with each new event potentially leading to catastrophic consequences for any existing life form. As a result of this bombardment, surface materials were constantly recycled, and new craters formed by impacts became sites where chemical reactions could occur, necessary for the formation of the first organic molecules of life. This process led to Earth under the influence of cosmic forces constantly changing, and it was in these conditions that life began to evolve. During this period, according to scientists' estimates, around 100,000 different comets and asteroids may have crossed paths with our planet, leaving behind not only craters, but also remarkable traces in the history of our planet's formation. Approximately 4 billion years ago, Earth experienced a period known as the Late Heavy Bombardment, as described by historians and astronomers. This phenomenon was characterized by a sharp increase in the number of celestial bodies crashing into the surface of the young planet. For several hundred million years, from around 4 billion to 3 billion years ago, Earth was subjected to constant impacts from asteroids and comets, which could reach the size of modern countries. For example, one such object, known as Tikhon, had a diameter of about 130 kilometers and left a crater with a diameter of approximately 150 kilometers on the Moon, indicating the immense force of the impact. This period can be imagined as a true cosmic bomb, where large celestial bodies rained down continuously on the planet's surface, creating conditions that we can barely imagine. The impacts of such asteroids could melt the already solidified crust of Earth, resulting in the formation of vast magmatic oceans that could reach depths of several kilometers. Scientists such as Dr. Christian Fleischer from the Institute of Astronomy in Germany assert that these collisions could not only alter the planet's landscape, but also significantly influence the atmosphere and climate during this time. Particles ejected into the atmosphere could form dust and gas clouds, leading to substantial temperature changes. This was a time when Earth was essentially young, forming under harsh conditions, and such catastrophic events played a crucial role in its evolution. Furthermore, some scientists suggest that it was during this period that the first processes leading to the formation of oceans occurred, when water was released from the planet's interior as a result of impacts. These events not only shaped the geological structure of Earth, but also created conditions favorable for the eventual emergence of life. At this time, the planet showed no signs of life, only vast, gloomy, and desolate landscapes where each new impact left deep scars. Such conditions laid the foundation for the creation of elementary molecules necessary for life, gradually transforming Earth into a planet capable of supporting life. About 30 years ago, scientists like Dr. Jonathan A. Hazen made significant strides in understanding these processes by studying lunar soil samples collected by the Apollo missions. These samples contain microscopic traces of elements that could have been ejected as a result of powerful collisions, allowing us to look back into the distant past. Scientific research shows that it was during this time that important minerals such as olivine and pyroxene formed, which became the basis for the formation of Earth's crust. Meteorite bombardment in the early days of Earth played a crucial role in the formation of its water reserves. It is believed that between 4.5 and 4 billion years ago, the planet was subjected to intense impacts from icy comets and water-rich asteroids. These celestial bodies, acting as messengers from distant space, brought with them precious liquid in the form of ice or chemically bound in minerals, such as hydrated minerals. For example, comets composed of a mixture of ice and dust could contain up to 30% water by mass. Studies show that many of the comets that collided with Earth had orbits that passed through the Kuiper Belt, where they formed. The impact of such comets on Earth's surface occurred gradually over millions of years, and as they penetrated the planet, they melted their icy cores, releasing water that then accumulated in oceans and seas. Asteroids such as Type C also contained significant water reserves in the form of hydrates, further contributing to the replenishment of the water balance. One of the most well-known examples is the asteroid Bennu, which, according to the OSIRIS-REx mission, contains organic molecules and water, confirming the theory that such objects could have provided early Earth with the necessary components for life. Thus, drop by drop, meteorite by meteorite, the future water reserves of Earth were formed, which became the basis for the emergence of life. Estimates suggest that as a result of meteorite bombardment, up to 100 million to 1,000 million tons of water could have reached Earth, which is a significant portion of the total volume of water we observe today. Studies show that it was during this period that the first oceans began to form on Earth, providing the impetus for the further development of the biosphere and ecosystems. For instance, in 2020, scientists from the University of Texas presented data suggesting that comets and asteroids could have provided up to 90% of the water on Earth. The gradual accumulation of water created the necessary conditions for the formation of the atmosphere and climate conducive to the emergence of life. The process of forming the primary oceans on Earth was long and complex, spanning millions of years. At the beginning of its history, approximately 4.5 billion years ago, Earth was a molten sphere with intense volcanic activity on its surface. The atmosphere contained water vapor, which was produced by volcanic eruptions and comets falling onto the planet. As Earth cooled, this water vapor began to condense, forming clouds. Massive, prolonged rainfall fell on the surface, lasting for centuries, creating conditions for the formation of primary water bodies. These rains, intense and continuous, gradually filled in the depressions in the landscape, creating the first seas and oceans on the still hot planet. This was the time when water, as the primary building block of life, began to take shape on Earth. Around 3 billion years ago, when the surface temperature stabilized and water filled the low-lying areas, processes began that laid the foundation for the formation of the first simple forms of life. A crucial aspect of this process was that the oceans not only filled the space, but also became chemical reactors where elements necessary for the formation of organic compounds combined. Thus, in these primary water bodies, complex chemical reactions took place, eventually leading to the emergence of the first cells. These cells, in turn, became the basis for all the biodiversity we observe today. Concurrently, due to Earth's rotation and gravitational field, the oceans began to acquire their modern structure, forming continents and oceanic trenches. Gradual cooling of the planet and the influence of gravitational forces contributed to the formation of a stable climate, which allowed for further evolution of life in these primary waters. As a result of this process, by 2 billion years ago, the oceans had become deeper and more diverse, providing a variety of conditions for life. These primary oceans became home to the first microbes, which began to use solar energy and carbon dioxide for photosynthesis, which later altered the Earth's atmosphere. Thus, the formation of oceans became not just a geological process, but also the foundation for the emergence and development of life on our planet. The first rains on Earth, which appeared around 4 billion years ago, were far from what we imagine today's precipitation to be. These were acidic rains rich in chemical compounds that formed as a result of volcanic activity and mineral breakdown. Volcanic gases such as carbon dioxide, sulfur dioxide, and ammonia entered the atmosphere, where they reacted with water vapor. This led to the formation of clouds that eventually unleashed not just water, but a genuine chemical storm on the scorching surface of the planet. Imagine a relentless downpour with immense force crashing onto molten rocks, causing sizzling and explosive evaporation. Temperatures on the planet's surface reached around 1000 degrees Celsius, and upon contact with water, clouds of steam rose into the sky, creating an atmosphere of wild elemental struggle. These early rains could not bring life, rather they served as a catalyst for its emergence. Water falling from the sky mixed with minerals and acids, leading to the formation of the first bodies of water. But not with clear, transparent water, but with solutions where chemical substances boiled and churned. These processes occurred in an atmosphere not yet enriched with oxygen, under the glow of the sun, illuminating the scene where the fiery surface of the planet clashed with water falling from the sky. The fate of life on Earth in the future depended on these first acidic rains, as they created conditions for the formation of primary oceans, in which simple organisms could eventually arise. These rains were the first step towards the formation of complex ecosystems that filled the planet with life. A crucial point is that the chemical reactions occurring during these rains influenced the composition of minerals, which later became the basis for the formation of soil. As shown by research, for example, by John Hutton of the University of California, the composition of soil significantly changed in the first billion years of Earth's existence due to the influence of these acidic rains. Early Earth's bodies of water were essentially boiling pots, rich in minerals and chemicals that differed from today's oceans. These seas, which emerged around 3.5 billion years ago, were not only warm but also had murky, sometimes brightly colored water. This might seem fantastical, but these primordial bodies of water were indeed a chemical storm. The water could be greenish, yellowish, or even reddish, due to the high concentration of various salts and metals like iron and copper. These elements washed off the surface of young Earth, created unique conditions that in turn facilitated the formation of the first organic molecules. Experiments conducted by scientists such as Stanley Miller in the mid-20th century showed that in such conditions, the synthesis of basic amino acids was possible, which could indicate the birth of life. The boundaries of these primordial seas were constantly changing due to active volcanic activity and changes in topography. Volcanic eruptions released vast amounts of gases like carbon dioxide and methane into the water, contributing to the formation of acidic precipitates and altering the chemical composition of the bodies of water. These conditions created an unstable environment where sea levels could significantly fluctuate depending on geological processes. Water in these seas could actively evaporate, leaving behind salt deposits and forming new minerals. Scientists believe that it was in such conditions that the first microbial communities could have emerged, serving as the foundation for further life development on Earth. For example, in the vicinity of modern oceans like the Pacific and Atlantic, traces of these ancient seas can be found in the form of specific minerals that formed under high temperature and pressure conditions. In one such place on the ocean floor, scientists discovered concentrations of hydrogen sulfide sources, which may indicate the presence of such bodies of water in the past. In the primordial oceans, complex chemical reactions took place, creating unique conditions for the formation of life. Water, coming into contact with the minerals of the Earth's crust, actively interacted with them, dissolving various elements and creating a complex chemical broth. This broth resembled an ideal laboratory where, over millions of years, starting around 4 billion years ago, thousands of reactions occurred. The oceans were not just bodies of water, but true gigantic natural laboratories where various minerals, such as silicon and aluminum, interacted with the gases of the atmosphere. These reactions led to the formation of primary organic compounds, which later became the basis for the emergence of the first living organisms. Water in the oceans, rich in various minerals, acted as a solvent, allowing elements to mix and react with each other. For example, carbon dioxide dissolving in water formed carbonate compounds, contributing to the formation of new minerals and increasing the chemical diversity of the environment. It is important to note that these processes occurred under extreme temperatures and pressures, adding another layer of complexity to these chemical reactions. These oceans were dynamic ecosystems where each drop of water could contain millions of molecules participating in continuous interaction. As a result of these endless chemical changes, conditions were formed that were necessary for the origin of life, which later became the basis for the evolution of all living organisms on Earth. Research shows that it was precisely in such conditions, when water, minerals, and gas formed complex mixtures, that the first primitive structures capable of self-reproduction could arise. These early chemical processes that took place in the oceans became the basis for biochemical reactions that ultimately led to the appearance of the first cells. Thus, the primary oceans were not just places where water met the Earth, but active participants in the creation of life on the planet. At the bottom of the primary oceans, there existed hydrothermal springs that became underwater oases of heat and chemical activity. These sources, sometimes referred to as chimneys, are cracks in the ocean floor from which hot water, rich in various minerals, is ejected. The temperature of the water exiting these sources can reach up to 300 degrees Celsius, while the surrounding water is significantly cooler, creating a sharp contrast. For example, in the Black Sea, 20 kilometers from the coast, sources have been found that emit jets of dark, mineral-rich water enriched with hydrogen sulfide, making these places extremely interesting for study. Research conducted in 2006 by an expedition on the research vessel Natan Hale showed that these underwater chimneys can reach heights of up to 30 meters and represent unique ecosystems where organisms adapted to extreme conditions live. In such conditions, thermophilic bacteria and archaea thrive, using the chemical energy released during the reaction of hydrogen sulfide with oxygen to synthesize organic compounds, which form the basis of the food chain in these ecosystems. These microorganisms form dense colonies that can reach a thickness of 1 meter, creating a sort of underwater forests. Hydrothermal sources not only serve as habitats for unique forms of life, but are also key elements in understanding the origin of life on Earth. For example, experiments conducted in 2003 by scientists at NASA's Jet Propulsion Laboratory showed that conditions similar to those around hydrothermal sources can promote the formation of organic molecules necessary for life. Therefore, underwater chimneys are not only an amazing natural phenomenon, but also a crucial part of the ecosystem that continues to raise many questions for scientists. For instance, in 2009, researchers from the University of California, San Diego discovered that organisms near these sources can metabolize heavy metals, opening new horizons for understanding biochemical processes in extreme conditions. The formation of the first continents on Earth occurred around 2.5 billion years ago, when sections of lighter crust began to slowly rise to the surface of the mantle. These fragments of land formed from molten rock gradually coalesced to form small archipelagos that could be compared to tiny islands in a raging ocean. At this stage, the planet was still very young and its surface was a true geological arena where volcanic activity was ubiquitous. Exposed sections of crust could appear as untamed lava fields where craters spewed molten magma. There were no modern ecosystems, vegetation was absent, and the atmosphere was saturated with carbon dioxide and other gases, making the air toxic for most modern forms of life. The sizes of these early continents were significantly smaller than what we see today. Due to instability and constant geological processes, their outlines were constantly changing. Geological processes such as plate tectonics caused sections of land to shift or join together, creating new forms of relief. These formations could be either temporary or long-lasting, but in any case, they had nothing in common with the modern landmasses we know today. Periodic, catastrophic volcanic eruptions would spew vast volumes of ash and gases into the atmosphere, further complicating the conditions of life on these young continents. Scientific research shows that during this period, the speed of tectonic processes was significantly higher than it is now. For example, on some areas, the rate of oceanic crust expansion reached several centimeters per year. This created conditions for the formation of new seas and oceans between the emerging lands. Ultimately, these young continents began to evolve, leading to the formation of larger land masses that we can observe today. During the changes in relief, other important geological events also occurred, such as the formation of metamorphic rocks under pressure and temperature. These processes gave rise to the first ecosystems that began to form on more stable sections of land, although this was still far from the present. It is important to note that in the early stages of continental formation, there was no uniform structure. Each of these lands was unique in its composition and characteristics. These fragments of land, like pieces of a mosaic, gradually combined to form larger formations, but the formation of modern continents was still a long way off. On the early Earth, tectonic processes occurred with extraordinary intensity, creating a unique landscape of our planet's surface. The Earth's crust, composed of numerous fragments, was in constant motion, much like a mosaic where each piece and tile sought its place. This movement was driven by the immense internal heat left over from the planet's formation around 14 billion years ago. At that time, surface temperatures reached critical levels, allowing magma from the mantle to rise and form new lands. About 1 trillion years ago, when the Earth was just beginning to cool, volcanic activity was significantly higher than today, spewing volcanic gases and ash into the atmosphere, which was quite unlike our current atmosphere. This resulted in continuous changes in topography. Mountains rose and oceans deepened, forming new ecosystems. Considering that the Earth's internal heat ensured high magma fluidity, various crustal segments moved faster than they do now, leading to the formation of massive cracks and faults. This movement was uneven, sometimes causing large-scale disasters such as earthquakes and volcanic eruptions. Around 3 billion years ago, when the first continents were forming, tectonic activity was so great that the crust structure changed rapidly. As a result of this constant motion, mountain ranges like the Urals and Alps were formed and continue to grow in height. It is worth noting that in the early stages of planet formation, continents did not have clear boundaries and were scattered landmasses that later merged into larger continents. These tectonic activities were not only responsible for landscape changes but also for the formation of various natural resources. For example, the movement and collision of crustal fragments led to the formation of deposits of valuable minerals, such as coal and oil, which later became the foundation for human civilization's development. Ultimately, all this dynamism underscores that Earth is not a static surface, but a living organism that continually changes and adapts to new conditions. As a result, the mobile elements of the crust created unique geological structures that have existed for millions of years. Subduction is a process where one tectonic plate slowly descends beneath another, returning to the Earth's mantle. This mechanism operates like a gigantic conveyor belt, where the upper part of the crust, consisting of oceanic or continental plates, moves across the planet's surface. When it encounters another plate, it begins to gradually submerge. This process can take millions of years with a speed of just a few centimeters per year. For example, in the region of the Pacific Ring of Fire, where the Pacific and North American plates meet, active subduction is observed. Here, the Pacific plate, with a thickness of around 100 kilometers, slowly descends under the North American plate to a depth of up to 70 kilometers. This process not only forms deep oceanic trenches, such as the Mariana Trench, but also causes powerful earthquakes. On September 18, 2001, a subduction-induced earthquake of magnitude 9 occurred, resulting in a tsunami that claimed the lives of more than 20,000 people in Indonesia. It is important to note that subduction also plays a crucial role in volcanic activity. When an oceanic plate descends, it heats up and begins to release water, which facilitates the melting of the upper layers of the mantle. This leads to the formation of magma, which rises to the surface, creating volcanoes. For instance, the Krakatoa volcano in Indonesia is a direct result of such processes. Its eruptions at the end of the 19th century were among the most destructive in history. Subduction not only creates volcanic systems, but also mountain ranges. When an oceanic plate collides with a continental plate, it cannot completely submerge, resulting in the formation of mountains such as the Andes in South America. These mountains continue to grow as the process of subduction is endless, demonstrating how the Earth is constantly transforming under the influence of internal forces. An example of such growth is the height of Aconcagua, which reaches 6,999 meters and continues to increase. As a result of subduction, sedimentary basins also form where ancient marine deposits create rich coal and oil reserves. These processes, occurring over millions of years, create a striking picture where the slow movement of plates hides immense power capable of altering the planet's landscape. One of the most striking examples of such changes is the Nazca subduction zone, located off the coast of Japan, where plates collide with the threat of powerful earthquakes. In the early stages of Earth's formation around 4 billion years ago, active tectonic processes led to the formation of the first mountain ranges. When different sections of the Earth's crust collided, dense layers of rock were compressed and pushed upwards, forming mountain chains that appeared more like low, sharp ridges composed of dark volcanic rock rather than the majestic peaks we see today. These mountains slowly rose, gaining height over millions of years due to continuous geological processes. Unlike modern mountains, which are eroded by rivers and glaciers, the primitive ranges were exposed only to wind and rain, which significantly slowed their destruction. At that time, Earth's atmosphere was far from what it is today, acidic and rich in carbon dioxide, which contributed to the formation of harsh weather conditions, though not to the extent seen today. For instance, the modern Himalayas, formed by the collision of the Indian and Eurasian plates, have already been shaped by erosion into magnificent peaks, whereas in the early geological epochs, such processes were just beginning. During this period, the primitive mountain chains were little more than piles of rocks gradually shaped by elementary natural forces. This process, spanning millions of years, demonstrates that mountains are not static formations, but dynamic structures in constant motion. It is important to note that at the time these ancient mountain ranges were forming, continents were still in the process of creation, and the concept of Earth's crust was just beginning to take shape. These mountain formations became the foundation for future continents, which would subsequently undergo further changes. Scientific research conducted in the 20th century by geologists such as Dr. James Hutton confirmed that similar tectonic processes occurred on other planets, such as Mars, where traces of ancient mountain ranges were also found. It was established that mountains form not only from the collision of plates, but also through volcanic activity, which led to the creation of new landforms. Each new generation of mountains formed during this time bore witness to changes on the planet, and each mountain carried the history of climate and tectonic activity on Earth. These ancient mountain ranges gradually rising created unique ecosystems that would become the home for the first forms of life on the planet. The primitive mountain formations, such as the primary ranges in the territory of modern Western Urals, were merely forerunners of what would later become the basis for the entire geological structure of our world. Approximately 4 billion years ago, when Earth was just beginning its history, its atmosphere was a mixture of steam, toxic gases, and elements that offered no chance for life as we understand it today. Over the course of hundreds of millions of years, due to geological processes occurring on the surface and within the planet, the atmosphere began to gradually change. Intense volcanic activity, prevalent in the early stages of Earth's geological history, released vast amounts of gases into the air, creating a dense veil over the planet. These emissions, composed of water vapor and other compounds, interacted with the oceans, which at that time covered significant portions of the planet. As water entered the atmosphere, it began to condense, forming clouds and precipitation. This process, occurring over millions of years, created a sense of planetary breathing. The atmosphere became lighter and less toxic, gradually clearing. With each new volcanic eruption and interaction with water, the sky over Earth became brighter and less dense, allowing sunlight to penetrate through the clouds and illuminate the planet's surface. This lengthy and complex process led to the transformation of the once gloomy and oppressive atmosphere into the more favorable conditions for life that we perceive today. Over time, as a result of geological changes and interactions, Earth's atmosphere became less hostile, creating conditions for the emergence of life, which was a significant milestone in its long and complex evolution. Approximately 3.5 billion years ago, the first single-celled organisms appeared, which began to harness solar energy, thus contributing to the further enrichment of the atmosphere. Weathering is not just a simple process of destroying rocks, it is a complex and dynamic dance between water, rock, and air that gradually transforms the face of our planet. Each rainstorm, as it falls on the surface, enters into chemical reactions with minerals, extracting elements such as calcium, magnesium, and sodium. For example, the weathering of feldspars found in granites results in the formation of clays like kaolinite, which serves as the basis for porcelain production. It is important to note that chemical weathering occurs everywhere, from tropical forests to Arctic regions, where frozen water also has a strong impact on rocks. Water droplets penetrating cracks cause expansion and contraction, leading to further destruction. This process is particularly noticeable in mountainous areas where valleys are formed under the influence of precipitation. Water penetrating rocks dissolves minerals and carries them to rivers and oceans, altering the composition of the atmosphere. For instance, in the Appalachian region, where rain falls on limestone formations, it creates karst systems and underground rivers, resulting in the formation of unique ecosystems. Over millions of years, such weathering processes have led to the formation of sedimentary rocks that have become home to numerous organisms and sources of valuable minerals. About 15,000 years ago, at the end of the last ice age, weathering played a crucial role in shaping modern landscapes. As the glaciers melted, they exposed previously hidden rocks, creating new ecosystems and altering climate conditions. This global geochemical cycle not only changes the appearance of the planet, but also affects the composition of the atmosphere, introducing carbon dioxide into the air, which in turn influences the climate. Water interacting with minerals creates acids that promote weathering, and this process continues today, as it has for billions of years, transforming the world around us. In the upper layers of the atmosphere, the formation of the primary ozone layer began, marking a significant milestone in the history of our planet. This process started approximately 2.5 billion years ago, when solar radiation penetrating the atmosphere interacted with oxygen molecules, resulting in the formation of ozone. Ultraviolet radiation, reaching oxygen molecules, caused their dissociation and the formation of free oxygen atoms, which then combined with other oxygen molecules to form ozone, a molecule consisting of 3 oxygen atoms. This ozone, located in the stratosphere, created an invisible shield protecting the planet from harmful ultraviolet radiation that could have destroyed living organisms. It is important to note that without this protective layer, life on Earth might not have developed as we know it today. The formation of the ozone layer occurred gradually, with its concentration in the atmosphere increasing due to chemical reactions driven by solar energy. By 3 billion years ago, this process had created a strong enough ozone layer to prevent most ultraviolet radiation from reaching the Earth's surface. This protective screen became critically important for the future development of life, providing conditions for the emergence of multicellular organisms and ultimately for the appearance of animals and plants on land. The formation of the ozone layer is an example of how interactions between physical processes and chemistry can lead to significant changes in the atmosphere, creating conditions for life. Over time, the ozone layer continued to strengthen, its presence becoming essential for the further existence and evolution of living organisms on Earth. As life became more diverse, the ozone layer maintained a balance, protecting organisms from high levels of radiation that could have caused mutations and other negative effects. This protective mechanism became the foundation for the formation of ecosystems that we observe today, allowing complex forms of life to exist in various biomes. The ozone layer, which has become a symbol of planetary protection, continued to evolve alongside life, providing the necessary stability for the existence of diverse species on Earth. In the primordial oceans that formed around 4 billion years ago, simple molecules engaged in complex interactions, forming more complex structures. These molecules, in chaotic motion, absorbed energy from their surroundings, leading to their combination into new combinations. Imagine this process as a chemical dance, where molecules gather at a party under the sounds of energy impulses from lightning and ultraviolet radiation. Around 3 billion years ago, as molecules combined, more complex chains emerged, which became the foundation for further life development. These chains, formed in the conditions of the primary soup, began to create the first proto-molecules, which possessed self-replicating properties. Energy provided by lightning and solar radiation played a key role in catalyzing these reactions, converting simple molecules into more complex compounds, such as amino acids and nucleotides. This process was not random, but followed certain patterns that scientists began to identify in the late 20th century. For example, in 1961, the famous experiment by Stanley Miller demonstrated that by replicating the conditions of early Earth, one could obtain amino acids from simple substances using electrical discharges mimicking lightning. As a result, in this primary chemical context, molecules, like dancers on a stage, began to interact with each other, creating increasingly complex structures that eventually became the basis for biological systems. These molecules not only combined but also changed, leading to the appearance of diverse life forms. Each step in this chemical dance was crucial, as it ensured the transition from simple molecules to more complex systems that could later develop and adapt to changing environmental conditions. The process of combining and transforming molecules in the primary oceans became the basis for the emergence of the first single-celled organisms, which may have appeared around 3 billion years ago, and since then, the evolution of life on Earth began. The RNA world hypothesis considers molecules of ribonucleic acid as possible precursors to life emerging in the conditions of the primary oceans. These molecules possess a unique ability. They can not only store genetic information as DNA does, but also catalyze chemical reactions similar to proteins. This makes RNA ideal candidates for the role of the first living entities, balancing on the border between the non-living and living matter. This concept was first proposed in the late 1970s by biochemists such as Sidney Altman and Francis Crick, who noticed that RNA could perform functions previously attributed only to proteins. Experiments have shown that short RNA chains can self-replicate, hinting at their potential role in evolution. This discovery was a significant step in understanding how life could have arisen from simple chemical interactions. In conditions rich in organic compounds, RNA molecules could form as a result of complex chemical reactions. These molecules could form structures with self-replicating properties, distinguishing them from other chemical substances. Thus, RNA could have become the basis for the first proto-organisms, which could interact with the environment and adapt to changes. An important aspect of this hypothesis is that the formation of RNA was not a random process, but the result of a long chemical evolution, confirmed by numerous laboratory studies. For example, in 2005, scientists from the University of Texas demonstrated that RNA molecules could spontaneously form from simple precursors, such as nucleotides, in conditions mimicking early Earth. This discovery showed that RNA could exist in a form capable of interacting with other molecules, creating complex systems capable of interaction and information exchange. These RNA molecules became increasingly complex, creating predecessors of the modern genetic code and protein prototypes, ultimately leading to the appearance of the first cells. Thus, the RNA world hypothesis opens new prospects for understanding how life could have emerged on Earth and continues to interest scientists seeking to unravel the mystery of our origin. In this context, RNA molecules represent key elements that could have played a decisive role in the transition from non-living matter to living systems, highlighting their uniqueness in the evolution of life. The formation of the first cellular membranes from lipid molecules is one of the most significant stages in the evolution of life on Earth. These molecules, with hydrophobic, water-repelling, and hydrophilic, water-attracting ends, spontaneously organize into double layers in an aqueous environment. This process, known as self-organization, occurs because the hydrophobic tails of lipids hide from water, while the hydrophilic heads turn outward, creating a barrier. As a result, microscopic bubbles are formed which represent the primary cellular membranes. In terms of size, these bubbles can be as small as a few micrometers in diameter, but their significance is difficult to overestimate. They provided a protected space where more complex chemical reactions could occur. For instance, in these membranes, molecules necessary for the synthesis of RNA and other biomolecules could accumulate, creating conditions for the emergence of precursors to living organisms. This protective package not only separates the internal contents from the external environment, but also allows for the creation of localized conditions that facilitate biochemical interactions. Processes such as catalytic activity and metabolic exchange could develop in these microenvironments, marking the beginning of the emergence of the first cells. Lipid membranes also played a crucial role in maintaining homeostasis, enabling the organism to maintain stable internal conditions despite changes in the external environment. Research shows that under certain conditions, such as the presence of specific salts and temperatures, lipids can form more complex structures, including liposomes and microspheres, which serve as the foundation for the further development of cellular systems. This process of membrane formation, which occurred approximately 3.5 billion years ago, was a pivotal moment that opened the door to the further evolution of biological systems. In the process of forming the first protocells, which took place at the dawn of our planet, molecular systems began to gradually acquire properties characteristic of living organisms. This was not a sudden explosion, but a slow and subtle process, similar to a whisper in the ocean of chemical reactions, which continued for billions of years. Scientific research shows that approximately 3.5 billion years ago, in the Mesozoic oceans, the first molecules capable of self-replication began to appear. These molecules, possibly simple RNA, could copy themselves under certain conditions. Dr. Louise Brown from the University of Cambridge, in her work published in 2020, asserts that exactly such molecules became the precursors of more complex systems that subsequently evolved into the first cellular forms of life. At this time, molecules began to exchange substances with the surrounding environment, which became an important step in the formation of metabolic processes. For example, in oceans rich in organic compounds, reactions could occur that provided primary forms of energy for these molecules. It is important to note that this process was not unambiguous and linear. Molecules and their combinations competed with each other, leading to natural selection. As Professor John Murphy from Stanford University asserts in his work from 2018, this competition contributed to the creation of more stable and efficient molecular systems. Gradually, these systems began to respond to changes in the surrounding environment, adapting to various conditions and thereby increasing their chances of survival. One of the striking examples is the hypothesis of the primordial soup, proposed by Stanley Miller and Harold Urey in 1953. They conducted an experiment in which they modeled the conditions that existed on early Earth and found that under certain conditions, amino acids necessary for the formation of proteins could be synthesized. These proteins, in turn, became the basis for more complex biochemical processes. Thus, in the oceans of ancient Earth, molecules merged, creating the first rudiments of life, and this struggle for existence became the basis for further evolution. Scientists describe this process as a gradual blurring of the boundary between the non-living and the living, where each new molecule contributed to this complex and fascinating mechanism. It is important to emphasize that this slow and unnoticed process became the basis for the formation of the first protocells, which ultimately led to the appearance of more complex forms of life. As a result of this interaction in the oceans, molecules emerged that possessed properties allowing them to function as living organisms, and this process continued for billions of years. Stromatolites are the oldest known evidence of microbial life on Earth, dating back over 3 billion years. These unique layered structures formed in shallow seas due to the activities of cyanobacteria and other microorganisms. Stromatolites are low, mound-like formations on the floors of ancient oceans, growing extremely slowly, layer by layer, sometimes adding just a few millimeters each year. As microorganisms lived, they trapped particles of sediment, leading to the formation of these peculiar rocks that can reach several meters in height. The evolution of stromatolites reflects the earliest ecosystems on the planet, where microorganisms like cyanobacteria interacted in complex ways. They not only produced oxygen, which became the primary element for life on Earth, but also created habitats for other organisms. For example, in Australia's Hamilton region, stromatolites older than 3.5 billion years can be found. These formations are not only evidence of life's existence, but also important sources of information about ancient climatic conditions. Geological studies show that stromatolites varied in shape and size depending on environmental conditions, such as water temperature and light availability. In places like Moulton Bay, stromatolites form extensive reef-like structures that have maintained their shape for millions of years. Remarkably, some modern stromatolites can be seen in places like the Bahamas, where they continue to grow and serve as homes for numerous marine organisms. These formations are not only interesting for biological study, but also crucial for paleontologists seeking to understand how life on Earth adapted to changing conditions. Stromatolites provide insight into what early life on the planet looked like and how it might have interacted with its environment. As a result, these structures become more than just geological formations. They are true archives of life, preserving information about billions of years of evolution. Stromatolites are key indicators of climate and ecosystem changes, making them essential for understanding the historical context of life's development on Earth. Ancient cyanobacteria, which lived on Earth more than 3 billion years ago, were pioneers in the process of photosynthesis, which brought about a true revolution in the biosphere of our planet. These microorganisms, measuring only a few micrometers in size, possessed a unique ability to use solar energy to synthesize organic compounds from carbon dioxide and water. The process of photosynthesis in cyanobacteria is facilitated by pigments such as chlorophyll, which absorbs sunlight and transfers energy into chemical reactions. One of the most well-known species of cyanobacteria, nostoc, actively uses this mechanism to synthesize glucose, releasing oxygen as a byproduct. Over billions of years, these microscopic organisms gradually increased the concentration of oxygen in the atmosphere, creating conditions for the emergence of more complex organisms. Around 2.5 billion years ago, during a period known as the Great Oxygenation Event, the concentration of oxygen in the atmosphere reached levels that significantly impacted the existing anaerobic organisms. This was a breakthrough in the evolution of life, as the oxygen released by cyanobacteria became the primary component for the respiration of aerobic organisms. Furthermore, this process led to the formation of the ozone layer, which protected Earth from harmful ultraviolet radiation, opening new opportunities for the colonization of land. Research shows that cyanobacteria initiated a process that fundamentally altered the chemical composition of the environment, thereby creating conditions for the emergence of multicellular organisms. For example, during a period around 700 million years ago, when the oxygen level in the atmosphere reached 21%, multicellular organisms such as the Ediacaran fauna began to actively develop and adapt to the new conditions. Thus, cyanobacteria not only transformed the atmosphere but also laid the foundation for the future evolution of all living beings on the planet. Scientific research conducted by scientists such as Stephen M. Kaplan and his team confirms that the active photosynthetic behavior of cyanobacteria marked the beginning of a long process of forming an oxygen-rich atmosphere, which continues to influence the climate and ecosystems to this day. The Great Oxygen Event that occurred on Earth was one of the most significant turning points in the history of our planet. It marked the beginning of the atmosphere being filled with oxygen produced by photosynthetic organisms like cyanobacteria. This process did not happen instantaneously. It took millions of years for oxygen to gradually accumulate in the atmosphere, changing the sky from a dull grey to a vibrant blue. Imagine a planet where carbon dioxide and methane once dominated, hiding the sun's light and gradually dispersing, allowing sunlight to penetrate deeper into the oceans, which also underwent changes. Initially, oxygen dissolved in water, contributing to the formation of iron oxides and giving the seas a reddish hue. This process was not merely physical, it opened new horizons for evolution. However, the oxygen, which was a byproduct of photosynthesis, was toxic to most of the existing life forms, such as anaerobic microorganisms, which could not survive in the new conditions. The gradual accumulation of oxygen in the atmosphere created competition among living beings, forcing them to adapt or perish. These changes acted as catalysts for the evolution of new life forms, including aerobic organisms that could use oxygen to generate energy. Over tens of millions of years, atmospheric oxygen continued to increase, creating conditions necessary for the emergence of complex multicellular organisms that eventually populated the oceans and land. Although this process was catastrophic for many species, it laid the foundation for the diversity of life we observe today. Ultimately, oxygen, which was once toxic to many, opened doors to new possibilities, enabling the development of life forms that could not only coexist, but also thrive in the new conditions. As a result, a planet initially dominated by anaerobic forms of life gradually evolved into a world where oxygen became the primary element of the biosphere, leading to the emergence of complex organisms such as fish, amphibians, and eventually mammals, including humans. Red-banded iron formations found in geological layers are unique witnesses to the process known as the oxygen catastrophe, which occurred around 2.5 billion years ago. These rocks consist of alternating layers where iron and silica-rich sediments create a striking pattern reminiscent of striped fabric. In these layers, one can observe the reaction of dissolved iron in seawater with oxygen produced by cyanobacteria, the first photosynthetic organisms on Earth. This process led to the formation of iron oxides such as hematite and magnetite, which precipitated as sediment and accumulated on the ocean floor. Notably, these sediments can reach thicknesses of several tens of meters and form extensive layers that can be found in various regions of the world, including Canada, Australia, and South Africa. Geologists like Dr. Stephen Goodwin from the University of Texas assert that the analysis of these layers allows not only to assess the oxygen levels in ancient oceans, but also to reconstruct the climate conditions of that time. For instance, red-banded iron formations that formed approximately between 2.5 and 2 billion years ago provide insights into how the oxygen content in the atmosphere and oceans changed, which in turn paved the way for the development of more complex forms of life. These rocks can be considered a kind of geological diary written in stone, chronicling the great transformation of the planet and how oxygen became one of the fundamental elements supporting life on Earth. It is important to note that research shows that it was during this period that oceans began to acquire their characteristic blue color, which we observe today, leading to an increase in the number of photosynthetic organisms on the water surface. Additionally, banded iron formations also serve as indicators of changes in oceanic ecosystems, as their composition and structure are directly linked to the biological activity in the waters of that time. Therefore, red-banded iron formations are not only an interesting geological object, but also a key to understanding the complex processes that shaped life on our planet. The discovery of such formations continues to inspire scientists to conduct new research, allowing them to gain a deeper understanding of how the oxygen produced by the first organisms altered the face of Earth forever. The snowball Earth hypothesis suggests that at certain points in Earth's history, particularly around 600 million years ago, the planet could have been almost entirely covered in ice. This state could have been caused by significant changes in the composition of the atmosphere, including a decrease in the concentration of carbon dioxide, which led to global cooling. Geological samples show that even equatorial oceans could have turned into icy deserts, where the surface water temperature dropped below 0 degrees Celsius. The image of such an Earth covered in an ice cap is difficult to ignore the harsh conditions. Ice caps stretching from the poles to the equator, leaving only small oases of open water around volcanic islands. These islands could have been the only places where life could continue, thanks to the heat generated by volcanic activity, which prevented the water around them from freezing. In such conditions, survival was a real challenge for early forms of life. Organisms that could adapt to extreme cold became dominant. This was an evolutionary filter, selecting the most adapted forms of life. For example, simple organisms such as microscopic fungi and bacteria could survive by their ability to form spores, which remained dormant until conditions became more favorable. Studies conducted by scientists such as Jason Black and his team from the University of California have shown that during these times, oceanic ecosystems could consist of unique forms of life capable of surviving in conditions of light deficiency and low temperatures. These organisms adapted to life in icy waters became the basis for future ecosystems when the climate became warmer again. It is important to note that these climate changes did not occur quickly. The process could take millions of years, during which the planet underwent significant changes in its ecosystem and geology. Tectonic movements, raising new volcanic islands to the surface, and changes in ocean currents could create new conditions for life, ultimately contributing to the emergence of more complex forms of life. As a result, despite the apparent barrenness of Snowball Earth, it was in these harsh conditions that many evolutionary innovations could have originated, which became the basis for future biodiversity on the planet. Among other things, these conditions provided unique opportunities for studying adaptations that occur in response to changes in the surrounding environment. About 1 billion years ago, the first eukaryotic cells emerged, marking a significant milestone in the evolution of life on Earth. These cells are more complex than prokaryotes, which were the primary forms of life before their appearance. Eukaryotes are characterized by the presence of a nucleus containing genetic material and various organelles that perform specialized functions. The process by which simpler prokaryotes transformed into eukaryotes is called endosymbiosis. Its essence lies in one cell ingesting another, but instead of digesting it, a symbiotic coexistence begins. This is akin to the creation of a miniature city where each organelle plays a unique role, providing the cell with necessary resources and functionality. For instance, mitochondria, responsible for energy production, and chloroplasts involved in photosynthesis, originated from this process. Eukaryotes became the precursors of multicellular life, paving the way for the emergence of complex organisms such as plants, animals, and fungi. These new cells possessed the ability to specialize, meaning they could develop into various types of tissues and organs, creating the diversity of life forms we observe today. Around 600 million years ago, during the Ediacaran period, the first multicellular organisms began to appear in the oceans. This transition from single-celled to multicellular organisms was foundational in the history of biology. Eukaryotes, with their complex organization, became the basis for the development of all modern forms of life, and their diversity continues to amaze scientists and researchers. Each newly discovered species and unique ecosystem adds to the vast biological mosaic that began to form with the appearance of the first eukaryotic cells. The theory of endosymbiosis, proposed by scientists such as Lynn Margulis at the end of the 20th century, explains how some organelles of eukaryotic cells originated from engulfed bacteria. This theory suggests that during evolution, one cell was able to engulf another without digesting it, establishing mutually beneficial relationships. For instance, simple organisms like amoebas could engulf photosynthetically active cyanobacteria, which then became chloroplasts in plant cells. This process can be seen as a form of biological cooperation at the cellular level, where former competitors became parts of a unified whole, leading to the formation of more complex cellular structures. For example, mitochondria, responsible for energy production in animal and plant cells, also have their origins in ancient bacteria that were engulfed by the ancestors of eukaryotes. This is not an isolated case. Such unions could occur repeatedly, creating diverse cellular structures and functional systems. Research shows that during symbiosis, not only was there an exchange of substances, but also genetic integration, which increased genetic diversity and adaptive capabilities of cells. As a result of such collaboration, multicellular organisms capable of complex organization and specialization emerged, paving the way for the appearance of plants, animals, and ultimately, humans. For example, research conducted in the 2000s showed that the genomes of mitochondria and cyanobacteria share many similarities, confirming the hypothesis of our common origin. Thus, symbiotic relationships at the cellular level became the foundation for the evolution of complex forms of life that we observe today. Within this evolutionary process, it is important to note that symbiosis was not always peaceful. Competition for resources often led to conflicts, but it was these interactions that helped develop life on Earth. At the cellular level, there is a constant struggle for survival, and only the most adaptive forms of cooperation succeed, becoming the basis for further evolutionary changes. Over 800 million years ago, at the dawn of multicellular life, individual cells began to unite, forming simple colonies that became the precursors of today's multicellular organisms. These colonies consisted of cells performing specialized functions, allowing them to interact more effectively with their surroundings. For instance, some cells were responsible for photosynthesis, while others handled movement and protection. Unlike plants and animals, these primitive organisms were something intermediate, floating in ancient seas, and could be described as jelly-like masses gently swaying in the warm waters of the primordial ocean. They were incredibly simple compared to modern forms of life. Most lacked a clear structure and consisted of just a few dozen cells that simply attached to each other. One notable example of such organisms are simple colonies, similar to algae, which later became the basis for more complex forms of life. These colonies could reach several centimeters in diameter and formed underwater fields that attracted various marine inhabitants. It is important to note that these conglomerates of cells began to occupy various niches in ecosystems, and due to specialization, each cell could perform its unique role, significantly increasing the chances of the colony's survival in the face of intense competition for resources. Researchers like Australian biologist Dr. David Taylor, studying fossils of these organisms, concluded that this stage in evolution was the first step towards the emergence of complex multicellular beings, as it allowed cells to coordinate their actions, enhancing the overall efficiency of the colony. These colonies could have various shapes and sizes, which also allowed them to adapt to different environmental conditions and provided the diversity that would become the foundation for further evolution. They were neither fully plants nor animals, but occupied an intermediate position, demonstrating how evolution could use different strategies to achieve success in the struggle for survival. During their existence, these primitive organisms laid the groundwork for future biodiversity, as evidenced by fossil finds dating back approximately 600 million years ago, where scientists discovered traces of these first colonies in marine deposits. The Ediacaran biota, which existed approximately from 600 to 500 million years ago, is one of the most enigmatic chapters in the history of life on Earth. These were the oldest known multicellular organisms, which bore no resemblance to anything we know today. Their form and structure were remarkably different from the familiar animals we see now. These creatures were flat, soft-bodied, and resembled leaves or feathers with sizes ranging from several centimeters to over a meter in diameter. On the seafloor covered in soft mud, one could observe these strange beings gently swaying with the currents, like seaweed, but their bodies lacked the rigid structure found in modern animals. The Ediacaran biota inhabited a world without predators, and life evolved under conditions far removed from those of today. During this period, there were no hard skeletons, making their existence even more alien to our understanding. Scientists such as Australian paleontologist David G. Smith note that these organisms could have been the ancestors of modern multicellular life, but their exact place in the evolutionary chain remains uncertain. For instance, some of them, like Dickinsonia, could reach lengths of up to a meter and had a segmented structure, which raises questions about their relationship to modern animal groups. This paints a picture of a seafloor teeming with these mysterious organisms, which existed in a time when life was just beginning to explore multicellularity. Their way of life was likely tied to filtering food from water, which also distinguished them from later forms of life that developed predatory strategies. The Ediacaran biota opens a window into a world where life was entirely different from what we are accustomed to seeing. These creatures have become key to understanding how life on Earth evolved before the appearance of the first hard-shelled animals like trilobites, which emerged around 540 million years ago. The existence of these ancient organisms establishes a new temporal scale for understanding the evolution of multicellular life and how it adapted to changes in the environment. The Ediacaran biota contributes significantly to paleontology, becoming an important subject of study for scientists investigating early forms of life. For example, in the year 2000, traces of these organisms were discovered in Australia, with an estimated age of over 500 million years, confirming their existence in a time when continents had not yet assumed their modern positions. Research indicates that Ediacarans could have been not only the ancestors of modern forms of life, but also a unique branch of the evolutionary tree that did not leave descendants in the form of known organisms. Studying the history of our planet, it is impossible not to ponder how Earth has evolved from a molten sphere to the cradle of life. This process was incredibly long and complex, spanning billions of years. Initially, our planet was subjected to constant meteorite impacts, existing in a state of thermonuclear chaos with high temperatures and pressures. Gradually cooling, Earth formed its crust and oceans, which became the foundation for the emergence of primitive life forms. These oceans, filled with chemical compounds, served as the stage for the first biochemical reactions that ultimately led to the formation of simple organisms. The uniqueness of this path lies in the fact that each stage was critically important for the formation of the ecosystem that exists today. As life developed, it adapted to changing conditions, including ice ages and mass extinctions, which caused significant changes in the biosphere. Thus, we observe how life has evolved from single-celled organisms to complex multicellular forms such as dinosaurs, mammals, and ultimately, humans. Each of these stages has left its mark both geologically and biologically, forming the diversity we see on our planet today. In this remarkable story, the fragility of life becomes apparent. Despite all the complexities, we now have the opportunity to study this evolution, lying in our beds, reflecting on how the first glimmers of life emerged in the depths of ancient seas. We can only imagine looking into the dark depths of the oceans in those distant times, where the first organisms were born, from which all existing forms of life have since evolved. Good night, and deep, peaceful dreams of ancient seas and the first glimmers of life on young Earth.